Welcome to today's class. My name is Ms. Tessler. Today, we'll be identifying and drawing lines of symmetry in two-dimensional figures. Here's what you'll need for class today. Pause the video and gather your materials. Ready, set, let's go. We'll start with our pentagon template. What do you notice about this shape? Maybe you noticed it has 5 sides, 5 corners, or maybe you noticed its angles. It has 2 right angles, 2 obtuse angles, and 1 acute angle. We're going to cut out the pentagon, but first, fold your paper in half like this, so the dotted lines are on the outside. Take your time and line up the edges of your paper as best as you can. Then, cut it out on the dotted lines. Watch what happens when you unfold the pentagon. Do you see this line right down the center where we folded? Notice how both sides of the shape seem to match up exactly when it's folded on that line. I wonder, can you fold the pentagon any other ways that will make the parts match up exactly? Pause the video here, try it out, then tell me what you found. Hey, welcome back. Did you find any other ways to fold the pentagon so that both sides matched up? Yeah, me neither. So, this line we found must be pretty special. Using a straight edge for precision, let's trace that line. Great, now we have that special line recorded. I'm also going to keep track of what we find today in a chart. So on the pentagon, here is the line we found that split the shape in half, and there was just 1. Now you can set your pentagon aside. I bet we can find other shapes that have more than one of these special fold lines. Grab one of your pieces of paper. What shape is the piece of paper? It's a rectangle. Try folding the rectangle as many ways as you can. The goal is to find spots where, when folded there, the 2 halves match up exactly. You can try matching up sides, matching up corners, anything you can think of. When you find a fold that works, use your straight edge and trace the line. How many do you think you'll find? Pause the video for as long as you need. I'll meet you back here. How many fold lines did you find? I found 2. Does yours look like mine? 1 here and 1 here. Let's add that to the chart. On the rectangle, we found 1 line here, 1 line here, for a total of 2. 1 more like that. Take another piece of paper. This time, we're going to turn this paper into a square. How do we do that? Follow along with me. First, fold one of the corners over until these edges match up just right. You might notice a triangle and a rectangle. Very carefully, cut off the rectangle. Then unfold it, and you have a square. And it looks like we found 1 line together. How many more do you think you can find? Remember to trace them as you find them. Pause the video for as long as you need. How many lines did you find that created matching parts on the square? I found 4. On the square, we have 1, 2, 3, 4 special fold lines. That's more than the pentagon and the rectangle put together. What is so special about the square? The square has 4 right angles, but so does the rectangle. What else is special about the square? Yeah, on the square, all 4 of its sides are the same size. That must be important. Keep this in mind as we look at a few more shapes together. Here are 2 more shapes. One is called a parallelogram. The other is called a rhombus. What do you notice about these 2 shapes? They both have 4 sides. I don't see any lines that are perpendicular, but I do see lines that are parallel. Here, and here, here, and here. On the parallelogram, these 2 sides look like they might be bigger than these 2 sides. On the rhombus, I'm not so sure. Take a moment to think and then tell me, can these 2 shapes be folded to make matching parts? Where and how many times each? Pause the video here. You can sketch the shapes on paper or your personal whiteboard and draw where you think the folds should be. Let's try the parallelogram first. Hold up on your fingers. How many fold lines do you think this one has that will make matching parts? Interesting. Let's try it. Maybe I can match up the top and bottom. Nope. These parts stick out. What about the sides? Do you think the sides will work? Can't match them up. Maybe the corners. Nope. Nope. I didn't find any. Maybe the rhombus will work better. Hold up fingers again. How many times do you think we can fold the rhombus and make matching parts? Let's try. I'll match top and bottom first again. Nope, just like the parallelogram. Side and side? Nope, that doesn't work either. Okay, what about the corners? Awesome, that makes 2 triangles. Those 2 parts match up. What about the other corners? Those parts too. These 2 parts make triangles too, but a little bit different. Anywhere else? I think that's it. On the rhombus, we found 1, 2 lines. On the parallelogram, we didn't find any places we could fold to make matching parts. On the rhombus, we found that we could fold it here and here. We found 2 lines. The rhombus and the parallelogram look very similar. Why do you think we could fold the rhombus this way, but not the parallelogram? When we folded the shape to find parts that match, we can say that these 2 sides are the same size as each other, and these 2 sides are the same size as each other. When we fold this way, we can say that these 2 sides are the same size as each other, and these 2 sides are the same size as each other. On the rhombus, that tells us that all its sides are the same size, kind of like the square. If the square got blown over by a really strong wind and its sides went like that. Do these two shapes have right angles? No, they don't. So maybe with less right angles, like the pentagon, we have less ways to fold the shape and make matching parts. The last shape we'll do together is a circle. Think for a moment. How many times can we fold this shape and make parts that match? That's two. It kind of looks like a circular pizza that's sliced. But I've seen pizzas with more slices than this. Do you think we could do more? That's four so far. I wonder if we could do even more. It looks like anywhere we choose to fold the circle, we can create matching parts. Why could that be? Something special about circles is that they don't really have sides. A circle has a round edge made up of points. And remember that points are tinier than we can even imagine. The special thing about those points is that every one is an equal distance from the center. Watch this. We could keep going. Now imagine an oval. An oval is also a round edge made up of points. Can you sketch an oval with me? Do you think that we could fold the oval as many times as the circle and make matching parts? Maybe a few times, but not as many times as the circle. This part is much wider than this part. So each point on the edge of the circle is the same distance from the center. Is the same true for the square? Even though all the sides of the square are the same size, the distance from the center is different in different places. So, knowing that every point around the edge of the circle is the same distance from the center, how many times can we fold the circle to make matching parts? If we fold the circle on any one of those points, as long as we cross through the center, we can make matching parts. And how many points are there in the circle? Since they're tinier than we can even imagine, there is an unlimited or infinite number of points. That means we can fold the circle an infinite number of ways to make matching parts. We could go on forever. That's pretty special. The last shape on our chart, the circle, we tried a few different ways, but then we learned that we could go on forever. These lines we identified today have a name. They're called lines of symmetry. Can you say that S word after me? Symmetry. When two parts match up, we call the two parts symmetrical. So we could say that this side and this side of the rectangle are symmetrical. We could say that this side and this side of the rhombus are symmetrical. When two parts of a shape are symmetrical, we also can say that the sides that match up and the angles that match up are the same size. Have you ever made a paper airplane and folded both sides to look exactly the same? If you have, you are thinking about a line of symmetry. Now that you know all about lines of symmetry, I think you're ready to try the problem set. The must-do problems are on the screen. Set a timer or watch the clock for 10 minutes and work on these problems. If you finish the must-do problems before time is up, feel free to work on any of the other problems in the problem set. Today, you learned to identify and draw lines of symmetry in two-dimensional figures, and I might never look at the world the same way again. Symmetry is in art, buildings, nature, all over the place. I hope what you learned today helps you see the beauty of the math that's all around you. Until next time, see ya!